All right, I have been doing studying on colors, and colors are primarily a function of transition metals. And once again, I started to look into the phosphors, and again, its phosphors are often transition metal compounds or rare earth compounds of various types. And they have a characteristic that I am about to show you, and Dave Hudson did some very good research on this, deep research. And I don't think he fully understands what he sees, but I think I do right now from looking into this and the transition metal reactions that I've been witnessing as a function of studying mud fossils. So let me show you what happens in these phosphors and the spikes of energy they give off, which we see on the old used to be CRT screens, cathode ray tubes. And a beam of electricity would sweep across, and it would hit these little red, blue, and green phosphors, and it would turn it into colors for your color TV screens. Now, of course, they're different now. They use different technology, but that's the old style. Now, I'm going to show you some information about this. Okay, this is who this work is attributed to, these pictures of the energy that CRTs give off. Now, let's see if we can see this a little better here. Hold on one second. I'm going to show the work that he did, or whoever a person may be. Now, it's on Wikipedia. It's easily found. Now, as you can see, you have the blue, the green, and the red phosphors. Now, look at this, because this is the interesting part. This is, you see this? This is intensity of the counts, they call it. In other words, it's how much brightness you're going to have. Now, look at this. You see this dead center here? Then you have little, bigger, bigger, then bigger, then bigger. And then right in the middle you have the blue. Right in the middle again you have the blue. I believe that this is transition metal related, and there are multiple jumps in the red phosphors, and there is multiple jumps in the blue phosphors, and there is very little in the green phosphors. And why? The green is the one I'm interested in because it doesn't display the same characteristics, except way, way, way out here. There's a little bump of green. I guess there's a little bump of green in here, but there's nothing like the others. So the green has some characteristics that the others do not, or vice versa, however you want to look at it. So that's what we want to look at, is the chemistry of the green. Whoops, I dug in a little deeper, and there is some other. There's the green right in the middle of the blue, and there's the green right at the top of the blue. So there's a bump here, and then the final bump is out here as far as I'm concerned. And you can see these little blue bumps in here. There's some kind of a pattern going on between these three transition metals and their orbitals, because this relates to the orbitals. And this nanometers really is like the distance from the nucleus, that type of thing. It's really the wave, the distance of the wave from trough to trough. But it's, you can think of it in distances from the nucleus. Something has to exist here. All of these three exist in that same exact range. These all exist in that same range. You know, these other ones have different ranges here and there, but they seem to occupy the same ranges in space. So there must be a certain distance from the nucleus that all of these things reside, because otherwise they wouldn't give off this same wavelength of energy. That's my thinking. Alright, anybody that's familiar with the mud fossils has seen this many, many times. These are the different colors that you see in the rocks of the earth, which are literally, these are the components that are in blood. It's just a fact. Transition metals are the way you can live, and the reason that you live is because you can transfer things and you can hook them onto these groups of these transition metals, so that you can have your oxygen goes in with your hemoglobin, which is the ferrous oxides, and it adds an oxygen here, takes one off over there, transfers it into your tissues, removes the carbon dioxide, does all kinds of things, takes out things in your urine, and all the acids of your stomach, do all kinds of things. It's amazing, and you need certain negative ions and so forth, and different acids and alkaline solutions in your body to do things. It breaks down the food with the acids, and it buffers it back out with alkaline things in your intestines, and all kinds of chemistry in your body, and it's from these things right here. So there's a couple different ways these things work. I'm going to show you some more about this. Alright, I did this video a while back on Dave Hudson, and I show just to give us some idea that I do have some background in this. Now, I studied his work on gold, and it's monatomic gold, and it was extremely interesting. I did 2 videos on it. This is one of them, and this just shows that I have some background in this. Now, it comes out to where this is gold that's in rock. Now, I'm going to show you what his research is. Hold on one second. All right, this is a geode, and most people know what they are. They're bone ball. Well, they think they're just rocks, and they have holes in the middle of them, and they grow crystals. Well, they're literally biological entities that are either bone balls, which are hollowed out bones as they boil in geothermal areas, or they are tendinenthesis points, which is what this is. This round ball is a tendinenthesis point, and they boil out, and they end up with a cavity inside, and the cavity contains transition metals, which are in the blood of every living creature that has blood in it, and the blood has metals, and the metals grow crystals just like sugar does in rock candy in water, and these do the same thing inside these balls. And this is a bone ball. You see that? That's a vein, and that was where the artery was. The black is the black blood that comes out of the arteries, and that's the I'm sorry, this is the artery side, that's the vein side. Vein has the black blood. Anyway, what happens is when these boil out, they boil the contents out of here, and a lot of the contents may contain metals, which are the platinum group metals, gold, silver, platinum, all that business. Now, what happened was Dave Hudson found these deposits of this white, crusty stuff that boils out of these bone balls, and he found it was loaded with a ton of gold. And he found out there was tons of gold in it compared to what everybody else was mining. He could come up with a ton of precious metals, and I think I understand how the monoatomic gold is forced out of this stuff. That's where I'm looking at, is the monoatomic gold. How is this stuff processed? What is that heat doing? What is happening with these transition electrons? And I'm going to show you what I think is happening. Alright, this is David Hudson. Now, he creates what's called Orimus, which is monatomic gold. And he found this white powder, and it contains all kinds of metals and minerals in this white powder, and he realized it. And what I am saying is that is what boils out of bone balls and all of the creatures' bodies, and it collects in this white powder, like the residues it collects in your pan when you boil water. Now listen to this, because he did a lot of research. Now I'm going to try to explain what this means, and it's a little technical, but just listen to him.
All right. Once we had done the spectroscopy, and I did this for like 6-7 months, did all sorts of analysis with Ziggy. Ziggy became very arrogant. He said, look at what I can do. I can prove that these elements exist. I'm going to be famous. And so he goes over to Germany, and he talks to all his spectroscopical friends, and there was actually articles written in magazines about him over in Germany that he had discovered that these naturally occurring platinum metals were in Arizona. But he never could find anything that analyzed anywhere close to what he had analyzed for me. He analyzed the best material he found with analyzing 10 to 12 ounces per ton.
All right, I'm going to put this on hold 1 second. This is the key. David Hudson found the concentrated gold metals, so he knew where it was, and he knew what to look for, and I also know what to look for. But anyway, listen.
Okay, mine was like 2,900 ounces per ton. Okay, big difference. Anyway, he said, Dave,
you could mine this stuff right out of the dust.
I'm going to take this. I'm going to promote with it. I'm going to raise money. He went up to the Las Vegas area and worked with some people up there in Nevada. And then after working with the people in Nevada, I heard the information and moved up to Oregon, Washington area. I mean, it's just amazing how like spiderwebbed out the information after he started promoting with it. Unfortunately, Siegfried Brimmer has died and he isn't with us anymore, but it's part of my history, so I'm giving it. One of the problems we had, and I really can't be more specific, I want you to understand this, is the procedure according to the Soviet Academy of Sciences, the Vernadsky Institute for Precious Metal Research, that when you get the elements separated, you do a hydroxide precipitation, you drop it out of solution as a hydroxide, you filter it, water wash it, then you put this into a tube furnace.
All right, let me just explain to you what he's doing here. They are extracting what he's considering to be the heavy metals out of there, and then they're putting it into a tube furnace, which means they're putting it into an enclosed area so where they can burn it off to find out what kind of molecules are in, or atomic structures. Hold on.
Now, tube furnace is actually a quartz tube, glass tube. It can be this size to this size. But the tube goes through a furnace that has a round opening in it. And you actually put the tube inside the furnace, then you take this little porcelain boat, or some people use metal boats, but porcelain, fire clay or whatever. Anyway, we were using high temperature porcelain boats. Put the powder that you just taken out of the solution, you put it in this boat, you take a little metal push and you push the boat into the center of the furnace, where it's in the heating zone. You put a stopper in the end of the tube, and then you hook up a glass line and then a rubber hose that brings oxygen, argon, hydrogen, whatever gas you want. Well, according to the Soviet Academy of Sciences, you heat it under oxygen up to 800 degrees, and it forms an oxide. And then you put an inner gas in there, usually argon, to get all the oxygen out, and then you put hydrogen in. And then you hydroreduce for 15 to 20 minutes, and then you cool it down under hydrogen if you want a hydrogen compound. But if you want all the hydrogen out, you cool it under an inert gas like argon or helium. You cool down the ambient temperature, then you reach in and take the cork out, reach in and pull a sample out, and you put it on a scale and weigh it.
I'll listen to this.
Okay, we did this. But when we hydroreduce it and then cool it under argon, we pull it out in the air, and we took this cool sample, which is now room temperature, and placed it on our scale. And we have a little digital scale that weighs down to micrograms. And we put it on the scale. But the weight of the scale, just said the numbers are just running like this, like a slot machine.
It's going up.
The weight is changing continually.
It's growing crystal.
And John says to me, Dave, when do I record the weight? Now? Now? And this is just driving this PhD crazy. He said, Dave, this makes no sense. Well, if you actually take the sample and put it under a stereoscope, a microscope, three-dimensional microscope, you actually can see that, and it's actually forming crystals and growing right here in front of your eyes. And what it is the element is so reactive that it reacts with the air.
These are the transition metals.
And so it's pulling oxygen and water and nitrogen out of the air and growing crystals right here before your eyes. And you can see them moving and turning and twisting and as they form. It's alive, it's crazy. And John says, Dave, we have to get the real world. This is just like an approximation. This is not science. And yet we're following the procedure we're supposed to be following, right?
The Russians are very good at this stuff.
I've seen more octagon-shaped crystals than you can ever imagine.
They're almost all octagon.
Anyway, there's every shape in there because there's all the elements were in there, and depending on the element you're working with is what the shape was. But it was very reactive is the point, people. And it's actually hygroscopic. It picks up moisture and water crystallization, and it's continuous. It continues on and on and on and on for an hour, 2 hours, 3 hours. The color is still changing. And so you really get frustrated. And I said, John, and this is after months of this, every day we try weighing some of it.
He spent a ton of money.
Now you can imagine the frustration. I've tried to do good, solid science, and I said, there's got to be a real world here someplace. He said, Dave, there is an instrument. There's an instrument available commercially that was developed for the aerospace industry. It's called thermogravimetric analysis. And this machine actually is made out of a glass tube, a Pyrex tube, but inside the tube it has a heating element, and actually has a coil, a bifilar wound coil, so that to feel that heat actually cancel each other. And it has a little balance scale inside the heating area where you can put a sample in there under a controlled atmosphere. You could oxidize it, hydroreduce it, put inert gas on it, whatever you want, and it never hits the atmosphere. Never sees air or never sees the outside atmosphere.
So he puts an inert gas
and you
in
can
there.
weigh it while you oxidize it, weigh it while you hydroreduce it, weigh it while you put the argon on it, and then weigh it as you cool it down. I said, at least we will learn what it really is when we hydrogen reduce it, right? How much it cost? Well, they're about $350,000. And I said, well, I'll tell you what, can we lease them? And he says, yeah, you can actually go to Perkin-Elmer and they'll lease one to you by the month. And I said, well, let's lease one. I'll bring it in. So we brought this thermogravimetric analysis machine in, and John actually hired a master's chemist from England that had specialized in operating analytical equipment and instrumentation, because this machine was all computer controlled. So actually when you start the program, it will actually all on computer run the valves, run the gases, control the heat at whatever heating rate you program into it, turn on
This
gases
is
at what
science.
temperature you want turned on.
And you're
go
not
off,
doing
and
this in
shuts go
university.
off.
He's got to
It's
do
all
it.
computer controlled. But you needed somebody to understand computers. And most of us guys were not really computer literate, like I still am. Not computer literate. So this lady came in, I can't remember her name, I think it was Jan something, but I don't remember her last name. Anyway, she came in to run the TGA. Now when you lease this TGA, they actually give you analytical standards that you can actually put in the machine and check the machine with these standards. And they tell you exactly at what time, what temperature and the compound begin to break down and what the weight change should be, and then at what higher temperature it continues to break down and what the weight change will be, and you put the standard in to check the machine. And we put standards in, checked the machine, and everything worked really beautiful. So then we actually used the empty pan, we ran it to see, and everything went, it's just nothing changed, it always just stayed constant temperature. Then we put, and this was actually an iridium sample, and this is actually the transparency I used last time I spoke. But this iridium sample, there was 10.55 milligrams, which is not a big sample, it's a relatively small amount of material on the boat, and we started heating it. Now down here at the bottom is the temperature, and it goes up to about, what, 850 degrees approximately. Okay, and here is percentages, 100%, 75%, 50%. Okay, and so when we start heating at basically ambient temperature here, we start heating it, and immediately the temperature, the weight of it drops slightly. So by the time we got to 150, 160 degrees, basically the hydrogen was gone from the sample. And you can say it was fairly constant, or to right here is about, what, 600 and something like that. And about this time you see some hiccups, but generally what happened is it just drops off down to here. Now this is going from 100% down to like 60, what? That's 75, 50, that's about 60 something percent, 55 to 60%, just in the first heating. Now people, I can't explain this weight change when it was occurring. This was a dramatic weight change under an inert gas. That's the weight it should be right there. Now we just stopped right there, everything went fine. But we continue, here it goes, just right out here.
I'm going to explain this to you in a minute.
Then we decide, well, let's cool it down now from this temperature. All right, this is the cool down. All right, now, unfortunately, when you start to go backwards, wherever you're at when you start, that becomes 100%. Because you're going this way now, okay? So really ignore what this reads over here. The important thing is, wherever we were when we stopped the other graph, that's where we start this graph cooling down. And we're cooling this direction, going this way. And look at this. Now, we're doing the cooling at 2 degrees per minute.
It'll get more understandable.
Which is very slow. When you're at
explain
800 degrees, 2 degrees per minute, there's a lot of minutes. Between there and there is what? 340 or 350.
At certain temperatures,
You realize how long that
it's
is?
changing weight. It's changing
degrees
a
centigrade.
huge amount of weight.
Laboratory people always talk in centigrade. I grew up with Fahrenheit, but all the laboratory people talk in
And
centigrade.
they can't understand why.
Anyway,
and
you
it
realize where that
changes.
goes. If you project that all the way up here, and then it collapses, look at how far that goes. Now, everybody just said, well, there's something wrong with this machine. You know, something's gone wrong. There's just not reality here.
You see,
And you know, that
it was
does
here and
happen.
then
So we said, we got to check this. But just out of curiosity, once it settled down here, this is actually the same place it ended before. See, we started right there, cool, and actually right there is stable. Other than that one hiccup, which lasted about 4 or 5 minutes, it's basically stable. I said, well, tell you what, don't take it out. Let's just heat it again. And all the time we're under this inert gas, and it doesn't say what it was, what gas. But I'm sure it was heated.
every time they heat it, they're
There's argon
pushing
in it, one of the
another
two.
electron into
So
another
now let's just
transition
start right
state,
there,
is
and
what
heat it
my
again.
feeling is.
So this is now the starting point, 100%, which is actually 50-some percent. Let's start again. We start heating, and everything's fine for a while, and then these hiccups start again. And then look right here at this hiccup. Yeah, now this is going down. Now if you look at it, it's actually getting less and less and less and less and less weight, and then it goes right back to where it should be. And then less and less and less and less weight, and then it just collapses right back.
All right, I'm going to just stop it right here because it's kind of confusing. I understand that. But when we saw the CRT colors, the phosphors, which are transition metals, and we saw all those same sort of spiky little things, what's happening here is he's heating. Now, this is a different process, but it has the same result as the electron bombardment, although the electron bombardment is instantaneous because you're hitting it with electrons immediately and displacing those transition molecules, orbitals. Now, here he has to get it up to a certain temperature, see, and here the electron, I don't want to go, I don't want to go, I don't want to, and then the electron just jumps, or it somehow it gets less and less weight. So apparently that electron flew out of there somewhere, went somewhere, and then another one came back and took its place. Something along that line. I don't know precisely what to say about this, and I don't know why these drastic changes happen, but I do know that it's related. See it? Up, 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 up. It's got something to do with energy transition levels and energy orbital levels, which are the quantum states that these electrons are away from the nucleus, and we could see the spikes were interacting with each other. So there's something going on there. I don't have all the answers. I'm just looking at this stuff and seeing things that should be looked at. But what happened when Dave finished with his research, he could get it ends up pushing out somehow and creating a high energy molecule. So in other words, gold normally has to have two little bits of gold together, two atoms together, and it's two atoms create a single molecule of gold, and that is its normal state. It does not exist in a single state. However, he could drive it into the single state by pushing these transition level electrons upward, it appears, and then created a high energy state of gold. And apparently, this is what's said. All I can say is if it's in this high energy state, and these electrons somehow are pushed up where they're not supposed to be, and filling that orbital layer, which they normally don't, so you have the top level, the valence level, is normally not filled with electrons. Well, I think he's filling it because it turns into monatomic, which means it's not having to join up with its other normal other molecule. So that's the case. All right, transition metals. The atomic structure of them is like it's very intricate because it does not contain complete complements of electrons. In other words, you're supposed to have two in the first shell. These are the shells. And then you're supposed to get a certain number here and a certain number here, a certain number here, a certain number here. It grows, it grows, it grows. And they have to fill in every one of these shells. Now, transition metals do not follow that formula. There are shells in here that are missing electrons, and there's shells like gold only has one electron in the outer ring, the valence shell, which normally you would consider that highly reactive. However, because it's a transition metal, and I don't fully understand this, I admit I have no clue about some of this stuff, but I don't think anybody has a whole lot of clues either. These two electrons, though, attach in a diatomic gold. In other words, it becomes stable when this electron attaches with another electron. And that's because it has something to do with s orbital requirements. And then below, it has like a half a complement of electrons. I'll show you in a better formula. But the other thing you have to know is that we're only dealing with positives and negatives. The neutrons are not negative. They never were negative. I mean, they were always negative neutrons. Neutrons are not neutral. They don't just roll around on the floor. They're exactly the same as the electrons, only they're massive. And they're the same size as the protons, only just a little bit bigger. And what that means is that you have at least the same number of protons as you do electrons, and that means that you will have an excess negative charge in the center, and that means that you will repel shells of electrons away from the center because it's negative. Negative repels these negatives. So it keeps them at a distance. Then these will keep the next level at a distance away from them and splayed away from them in a certain crystalline formation. It's just the way it works. Now, what Dave Hudson did was he heated this thing so intently for such a long period of time that somehow he drove these electrons, like all of these electrons possibly, into the outer shell, and they finally stuck there. At first he brought them up and then they drop, and he brought them up and they drop, and then he brought them up and they drop again, and then all of a sudden he brought them up and they didn't drop. Well, the only thing I can tell you is that, to my way of thinking, he has accelerated them, and then they let go, and then they accelerate them back, and they let go, and accelerate, and then finally, for some reason, because they broke their lower bonds and leapt into here, or additional electrons came in and filled, or something from the nucleus of a negative nature popped out. I don't know, but all I can tell you is that the general effect of this is to have an extremely high energy atom. So think of it this way. This is literally decaying electrons. They're going to drop. They're going to drop. They're going to try to seek stability. When they drop, they give off light, literally light, because that's all it is. When light is only given off when something bounces up one or two layers or whatever, and then drops back down, and it gives off only this layer. So in other words, it requires enough energy to go way out to here, but when it drops back, it only drops off here, and it gives out this, and the rest is consumed as heat. Now that is what happens, and that's how light is affected. So what he's doing is heating. Now all of a sudden it's way up here. Now they say people eat this stuff and they turn glowy white, and I can understand that's possible, and that wouldn't hurt you either, because this is only electron energy. This is not like nuclear particles. Nuclear particles, everything is mass. If you drop a ping pong ball on your finger, it's going to bounce off your finger and you're going to be fine. But if you drop a bowling ball on your finger, you're probably going to be hurt. So the exact same thing here. You drop a bowling ball, which is a proton or a neutron, or you drop an electron. We're using electrons. They're dropping electron, and you'd be giving off some kind of glowy energy. I mean, that's just a fact. And you could probably eat this stuff, it wouldn't hurt you. And they say you eat it and you become healthier and does all kind of good things. And I could see it might do it, because there's energy there. There's energy there. That's what you live on, is energy. So that's all I can tell you, is what I'm seeing. Now let me show you some other stuff. All right, he gets real deep into this, but listen to what he has to say, and then listen to what happens.
That brings oxygen, argon, hydrogen, whatever gas you want. Well, according to the Soviet Academy of Sciences, you heat it under oxygen up to 800 degrees.
Soviets are
and
good.
It forms an oxide. And then you put an inert gas in there, usually argon, to get all the oxygen out, and then you put hydrogen in. And then you hydroreduce it for 15 to 20 minutes, and then you cool it down under hydrogen if you want a hydrogen compound. But if you want all the hydrogen out, you cool it under an inert gas like argon or helium. You cool it down to ambient temperature, then you reach in and take the cork out, reach in and pull a sample out,
Now this is the
and you
cool
put it on
part.
a scale and weigh it. Okay, we did this. But when we hydroreduce it and then cool it under argon, we pull it out in the air, and we took this cool sample, which is now room temperature, and placed it on our scale. We have a little digital scale that weighs down to micrograms. And we put it on the scale. But the weight of the scale, just said the numbers are just running like this, like a slot machine. The weight is changing continually. And John says to me, Dave, when do I record the weight? Now? Now?
He's making an extremely
this
reactive
is just driving this PhD
substance.
crazy. He said,
Extremely
Dave,
reactive.
this makes no sense. Well, if you actually take the sample and put it under a stereoscope, a microscope, three-dimensional microscope, you actually can see that, and it's actually forming crystals and growing right here in front of your eyes. And what it is the element is so reactive that it reacts with the air. And so it's pulling oxygen and water and nitrogen out of the air and growing crystals right here before your eyes. And you can see them moving and turning and twisting and as they form. It's alive, it's crazy. And John says, Dave, we have to get the real world. This is just like an approximation. This is not science. And yet we're following the procedure we're supposed to be following, right?
It's real science.
I've seen more octagon-shaped crystals than you can ever imagine.
All right, they're almost all.
Anyway, there's every shape
hold
in
on a
there because
second.
all the elements were in there, and depending on the element we work.
All right, I'm not going to bother going any further with this because he continues on about it. But the takeaway from this right now is that what he did was he took these transition metals and he heated them over and over and over again until they took on an extremely reactive, energetic form of molecular, of atomic orbitals. And it's apparently due to this transition metal compounds that have all of these extra places for electrons to reside or to move to. I'm not sure of the exact situation, but the only thing I can say is the only way this could occur is to have forced energy into these transition metals, and they're in such an energetic state as when they drop, they become stable. This is what happens, and it's almost like having a half-life. So as they drop, they become stable and try to find somebody to bond with, because now they're in a different molecular form and they're looking for somebody to fit into that molecular stability. And they just keep spitting out and spitting out and spitting out. And they do have some form of a half-life that could actually be measured, I'm certain. So he's found something here that should certainly be looked at. And the thing is that, you know, they're doing all this work on the outside of where they should be doing it. It's my way of thinking. Maybe they're doing some work that I don't know about, but I've tried to contact all the universities about all the things that I've discovered from mud fossils, transition metals, light, all of this stuff, and nobody even, they don't want to even contact you back. They don't have anything to do with you. So that's all I can say. This really needs to be looked at. This could be an extremely good power source. This could be the actually what you might be able to call an atomic battery, which, you know, there's extreme amounts of energy coming out of this thing. Something's got to be done with that.